So we're looking at populations, samples, and distributions. And some important things, a population is some major group that we're interested in. It's usually large. It's hard or impossible to get in contact with the whole population. Maybe it's fish in a lake, or all the people in town, or maybe all the people in the United States. So from the population, we have to take samples. So that's just a small group from the population. And when we do those samples, we generally want some kind of randomness involved in the sample. And taking random samples is a lot of work, so we just look at some of the basic ideas of what it means to be random and some different ways we try to achieve the randomness from a sample. We also want the sample to be representative, which means like the population. And the idea of a distribution is just the shape of a graph. And typically the kind of data we're looking at is quantitative data, right? Numerical data. And the kind of graph we're looking at is a histogram. And we spent a couple weeks playing with histograms, among other things. And a new idea related to this, we didn't get to last time, but we'll talk about today, is the idea of a sampling distribution. I'll try to show you guys some simulations that hopefully illustrate what a sampling distribution is. So generally, the most simple kind of sampling distribution is a distribution of sample means. So what that means is we have some sample size, like maybe n equals 100. And we take repeated samples of that same size. And then we just graph the mean of each sample. And see what happens. So we're going to do that right now with the help of a computer program. So I am going to share a link to a website we've been to a few times now. YouTube people in the future, this will be available in the description. So you can either search for StatKey or check out the link in the chat or in the description of the YouTube video. And what I want to look at here is the idea of a sampling distribution for a mean. Before I look at that, just backing up to last time, we've used this one categorical variable section here to look at histograms. And the idea, again, of a distribution, it just means what's the shape of the graph? How is the data distributed? And here I see a symmetric bell shape with a tail to the right. So this would be skewed right. The numbers here are the average lifespan of a certain group of mammals. We could look at the data if we wanted to. So we have baboon, some bears, beavers, dogs, donkeys, elephants, goats, moose. and the average age they live to. So pig can live to 10 years old on average. Rabbit's 5 years old on average. If we look at a different data set, we'll get a different distribution. So hot dogs, this is a bizarre one. What these are is there's a famous restaurant in New York, I think it's in New York, called Nathan's, and every year Nathan's has a hot dog eating contest. And so each number in the list here in the dot plot is the number of hot dogs eaten by the winner in a given year. So in 2004, 6, and 10, the winner ate 54 hot dogs in one sitting. That's insane. Anyway, here's that distribution. And the distribution changes a little bit depending on how you decide to group the data here. All right, so this one's kind of hard to describe. Maybe it's skewed left. Maybe there's a tail over there. That looks like a tail in that version. So just the point of looking at this here is just distribution. NBA players, blocks, bit more data here. So this is the, I believe, yeah, number of blocks, probably per game. Look up the data to double check. But we can see this data here is definitely, most players have a few blocks. So there's 0 to 50 blocks per game. And then there's quite a few players that have a lot more blocks per game. So this would have a right skew again. So distribution, what's the shape of the graph? And we had a few words we used to talk about that. Symmetric, bell shape, skewed left, and skewed right. So that's for a particular sample. Now here we're going to move on to the idea of a sampling distribution, which is multiple samples. So this one right here, let's look at the table. So back up a second. So again, I'm trying to illustrate what a sampling distribution is and how that's different from a regular distribution of data. So stat key, sampling distribution, mean. And the data set that I have here at the moment is baseball player salaries 2019. And if we look at the table here, there are 877 players. These are all the Major League Baseball players in 2019, and every one of their salaries in millions. So Martin Prado, $15 million in 2019 on his base salary. So everyone's base salary there. This is an entire population, okay? So these are all the Major League Baseball players. So this isn't a sample, this is a population. Now, let's suppose this is a population that we can't get everybody of, then what we would do is a sample. So right here, it says choose a sample size. I'm gonna make that a little bigger. I'm gonna make a sample size of 20 and hit OK. Then what I'm gonna do is I'm gonna ask the computer to generate one sample. So this generate one sample button. And what it's gonna do, it's gonna look at all of these 877 players here, and it's gonna randomly select 20 of them and tell me what the mean of those 20 is. So I'm gonna generate one. So from my random sample of 20, I got an average salary of 2.59 or 2.59 million. Notice the average in the population is 4.51 up here, and they calculate that for me. So I'm going to create another sample. So this is a different group of 20 baseball players. And this time I got an average of, oh, it's over here, 3.82. So when I click on one of these dots, it refreshes this sample table down here. So I'm going to generate another one. So I have a new sample. Maybe this one over here means 2.59. This one, 3.08. And this one is 3.78. Now, the idea of a sampling distribution is we do this over and over and over again. So we keep grabbing samples of 20 individuals from the population over and over and over. Every time we do that, we're going to get a slightly different average, and we're only care about the average. So we grab the 20 players, add up their scores, divide by 20, we just plot the average. That's it. If I do more of those, like 100 of them at a time, and another 100, you can see then the dot plot starts to fill out a little more. So now I'm actually going to do thousands of them. So every point on here is a different sample of 20 players. If I click on a point, it shows me the distribution down here, those 20 players. Now, like the original graph here, it's skewed right. Each sample is probably going to be skewed right a little bit. Now, it's a small sample. I only have 20. It's kind of hard to see on that screen, but that's what I got to work with at the moment. At the moment, I've generated 1,210 different samples. Each sample is 20 Major League Baseball players' salaries, and all I'm plotting here is the average. So I'm going to generate more, and more, and more. I'm going to keep going. I'm going to get like 6,000. Get there yet? There we go. So I have 6,000. Now, a couple things to notice about this graph right here. It's got a kind of a bell shape going on to it. There's a slight skew right. That happens for a couple reasons. My sample size is small, and the original population was extremely skewed right. Most baseball players make like 4 million or less, but there's a few that make more than that out here, and very few make more than 20 million or 30 million. That's unusual. And the idea of a sampling distribution is this mostly symmetric bell-shaped curve. And this is a curve we talked about last time. And the bigger the sample size, the more normal this is going to look. So what is normal? What do I mean by normal here? So just the importance of a sampling distribution. For a large enough sample size, and usually large enough means n is greater than 30. I went to 20. I'll tweak that in a minute and see what happens. The distribution should be relatively normal. So I mentioned that earlier. The question is, what does normal mean? I started talking about normal distributions last class. Normal distribution is a special type of symmetric bell-shaped distribution. So normal distribution has a symmetric bell shape. So here's what it means to be normal. Number one, symmetric bell shape. There's lots of distributions that have a symmetric bell shape, and they're not all normal. Now, if it has a symmetric shape, the mean and the median should line up in the middle. So they should be pretty much the same number right in the middle here. And the important things about a normal distribution is when we look for standard deviations on each side. So suppose we went 1 standard deviation on each side, and then 2 standard deviations on each side. And remember, standard deviation means average spread from the mean, average deviation from the mean. And then let's also look at 3 standard deviations from the mean. So -3 means 3 standard deviations to the left. And it's always the left of the mean. So if a distribution's normal and I look and count how much information is in between 1 standard deviation on the left and 1 standard deviation on the right here, I should expect to see about 68% of the data lives in between whatever those 2 numbers are right there. And we'll look at some examples of this in a minute. If I look within 2 standard deviations, so all of this, including the 1 standard deviation, I would expect within 2 standard deviations to have about 95% of the data from here to there. And if I look within 3 standard deviations, so all of the data, I think I'm going to get a highlighter for this one, in this region of the histogram, I should expect within 3 standard deviations to see 99.7. So all of the data from here all the way out to here, we should expect 99.7% of the data, so almost all of it. These percentages, along with standard deviations, are known as the empirical rule or the standard deviation rule. So that's the second thing that identifies something as normal. Also known as the standard deviation rule. And it's got 3 parts to it. We should find 68% of data within 1 standard deviation of the mean. We should find 95% of the data within 2 standard deviations of the mean. And then we should find about 99.7% of data within 3 standard deviations of the mean. So if a distribution has a symmetric bell shape and it meets these 3 percentages here with standard deviation references, then it's probably a normal distribution. And there are some things on their own that are normally distributed, but generally it's sampling distributions. And sampling distributions are needed to make predictions about data, especially in large groups, like if we looked at all of the 5th graders in the country, or all college students in the country, or all people, all adults in a given country. I'm going to redo this just to go over it again. Let's see, reset. I'm going to set the sample size to 30 this time. And then again, what happens if I hit 1, create 1 sample? The computer picked 30 of the baseball players from all 877, and it found the average and plotted just the average. And I could do that 10 times. So now I have a total of 11 different samples of size 30, and I'm only plotting the average each time. And what should happen is the average of all of these samples should hover around the average of the population. That's going to be this middle point. It's kind of magnetic, statistically speaking. And now I'm just going to do thousands of them. And it looks pretty similar to the one I made with 20. I'm starting to see a symmetric bell shape. But there's still a slight skew right for 2 reasons. 30 isn't a very large sample, and the original sample was very, very skewed to the right. But I'm still getting that symmetric bell shape. Now, in this case, they're making some calculations here for me. They're telling me how many samples I have. So I've made 9,000 samples roughly, each of size 30, and every dot here is the mean of one of those 9,000 samples. It says the average of all of those samples of 30, the average of the averages is about 4.5. Notice the mean of the original population was about 4.5. And then standard error is the standard deviation of these numbers right here. And it says the standard deviation is about 1.127. So here, what I'm going to do is take a look at two-tail, where I'm going to put 95% in the middle. And what should happen is I should expect that from the mean, this number 2.48 here is 2 standard deviations below the mean. And then this number on the other side here, the 6.903, that should be about 2 standard deviations above the mean. So I'm just going to double check to see if that happened here. And again, this is a computer simulation. It's like drawing cards. It's a little different every time. So I'm checking out what's called the empirical rule for means with a normal distribution. So the computer calculated that 95% of the data is this black region, and that 95% starts at 2.408. So any sample with a mean of 2.480 or higher gets counted, up to anything with a mean of 9.603. And these two numbers, according to the empirical rule, should be 2 standard deviations on either side, because that's what 95% goes with. This number right here is a standard deviation. So I want to see what happens if I take, like for this number here, that should be about the same as 4.507 plus 2 times 1.127. So I'm going to put that in the calculator, be right back with the calculator. 4.507 plus 2 times 1.127. Mistyped it. According to my calculator, I get about 6.76, so it's a little bit off there. Let's check the other number on the other side. So this number on the other side should be around 4.507. That's the mean, my center, but it should be minus 2 standard deviations. 1.127. And I enter that into my calculator and I get 2.253. So it's a little off. I was hoping it would be more on. And it's probably because I have this skewness over here that my sample size probably should have been a little bit bigger than 30. And usually the higher the sample size, the closer we get to those 95% with exactly 2 standard deviations. Let's try a different one. Statistics, no, auto centers, Olympic marathon, movie budget. Let's try that one. That is very skewed right too. NFL contracts, that's probably going to be skewed right. Is all the data here skewed right? Percent with internet access. Okay, that one's more uniform. Let's try this one. So this data set here, my recollection is from 2016, and it was, let's see, some world organization, I can't remember which one now, World Health Organization maybe, collected a bunch of data from each country. This data set right here is in a given country, what percent of the people had internet access in that year. There were 204 different countries, which was almost all the countries in the world at that time. So this is a whole population. And so let's do sample size of 30 again. And since this one doesn't have any skewness, I think we'll get slightly better results. And the more samples from the population we take, the more symmetric bell shape I should make. And it's always going to have some variation in it, like this one does. All right, I got up to 7,000. Notice again, so what is each of these points? So any point I point to here, if you look in the bottom right, is a sample of size 30 from the original population. So there's all these different ones. And what we should see is that the shape of those distributions kind of mimics the shape here. So this is almost like straight across. That would be called a uniform distribution. They're all almost the same height. But notice that whether I used a skew right distribution, like the baseball players, or a more uniform distribution, if my sample size is high enough, after I generate enough samples, I'm going to get this symmetric bell shape. And this symmetric bell shape should be a normal distribution. So if we look at that two-tail idea again, then what we should see is that, again, this is the standard deviation of this particular set of 7,000 samples, that if from 54.509 we go 2 standard deviations to the right, that should take us about to this number right here. Let's check that again. Let's try it. Another problem. So I want to check how close to the empirical rule we got. So the mean is 54.509. And if my sample size was big enough, 30, then if I take the mean and I add 2 standard deviations, and this is my standard deviation, 4.795, that should give me an endpoint here that marks this middle 95%. So check my calculator. And this one is a little closer, but still not quite there. So I'm close to this number over here, about 64, and that's almost 64. And again, that's marking about the right side of the middle 95%. And this number right here should be approximately equal to the mean minus 2 standard deviations. So minus 2 times that 4.795. Calculator says, mistyped something. What? There we go. 44.919. So not quite there, but close. So my calculation based on the empirical rule put me about right here. And this one put me about right here. And in those boundaries, we should expect to find about 95% of the data. And we're kind of close there. So is anything out there perfectly normal? The answer is no. But this idea of a normal distribution is a pattern that's been observed in a lot of different places. And the pattern is that when we graph it, it looks like a symmetric bell, roughly. If it's symmetric, then the mean and the median should be about the same. We played around with that a couple of times. And then if we look on each side based on the standard deviation, we should see about 68% for 1 standard deviation, 95% within 2 standard deviations, and 99.7% within 3 standard deviations. So where is this stuff used? It's used when people are making predictions about a population, like the percent of people that were voting one way or another in an election, for example, or the percentage of people who think the vaccine is going to help us out with COVID. Like, they didn't ask me, they didn't ask you, but they think they asked enough people that they know in general. Other places this is used a lot is with standardized tests. So let's take an example of some standardized tests. We're also going to take a look at the idea of the z-score, which I've talked about before, and we'll look at again. If we look at the math SAT, for example, the Scholastic Aptitude Test, it used to be used a lot for students leaving high school and going into colleges. It's been becoming out of fashion for several years now, and the pandemic kind of gave it a kick in the butt, and very few schools ask for an SAT score anymore. But usually with the SAT score, the mean For math scores, my recollection is it's been about 520. And the standard deviation, that's for the whole population, is usually given the symbol sigma. It's usually somewhere between 100 and 120. Let's call it 120 today. So, and a lot of students take the SAT. So there's a huge population, millions and millions, 100 million people take the SAT score, say. If we look at a graph of all the different scores that people got on the SAT score in the last few years or in a given year, what we should find is that the graph is a relatively symmetric bell shape. Right in the middle of that bell is the average. That would be 520 in this case. And then if we look out the standard deviation to each side, let's see, we go out 1, 2, 3 standard deviations to the right. And same thing on the other side, 1, 2, 3 standard deviations to the left. That would mean just jump by 120. So 500 plus 120 would be 640. 640 plus 120 would be 760. 760 plus 120 should be 880. Going the other way, subtracting the 120, that would be 400. And then 280. And then 160. Did I do that right? Plus 120. Plus 120. Yep, I think that looks right there. And again, what am I counting here? If I count by standard deviations, this 640 here would be plus 1 standard deviation to the right. This 760 would be 2 standard deviations to the right. This 880 is 3 standard deviations to the right. And remember what standard deviation mean? Standard deviation is a measure of average spread from the mean. So when we talk about standard deviation, we always have to reference the mean because it's related to the mean. The mean is 0 standard deviations from itself. It's the middle. Going the other way, 400 would be 1 standard deviation below the mean, so that would be negative 1 standard deviations. 280 would be 2 standard deviations below, and 160 would be 3 standard deviations below. Anytime we count standard deviations, those counts, 1, 2, 3, those are called z-scores. So all a z-score is a count of standard deviations from the mean. So if I made another number line down here, and I use these numbers to mark off the number line, then we could call this the z-axis. Z in statistics means we're counting standard deviations. They're called the z-scores. So let's suppose we took the SAT and we got a score of 760. Oops. So this is someone's score on the SAT. Compared to the mean, right, the mean is 520. So this person right here was above average. Okay? Now, if I take their score, 760, and I subtract the mean, 520, then I get 240. So they were 240 points above average. Now, a measure we use to talk about how far something is away from the middle is the standard deviation. So note here, my standard deviation, let's call it S, is 120. And if I take that 240 and divide by the 120, how many times does the standard deviation go into their above average amount here? Well, it goes in twice. And that 2 is the z-score. And all it means is 2 standard deviations above average, because it's a positive, and it's 2. Right, 240 is twice the standard deviation. So in general, one way to calculate a z-score for a specific number based on a data value would be to take the data value, usually we call that x, subtract the mean from that. That gives us the deviation, how far are they from center. Talked about deviation a while ago. And then divide that by the standard deviation. And that just makes a count of how many standard deviations we are. So you can kind of look at it graphically, you can look at it formula-wise. Because so many people take the SAT and it's kind of designed to be scores to be normally distributed. What we should find is that when we go and count all of the scores that are between 400 and 640 here, we should find that about 68% of the scores of the people live in that range right there. If we go out to 280 and 760 here, then we should find that about 95% of the people who took the test have scores between 280 and 760. If we did that one more time with the 160 and the 880, and we counted everybody that got a score 160 or higher up to 880, we should find that 99.7% of people had a score in that range there, based on the histogram. And again, if the scores are normally distributed. Welcome, Amy. We're playing with normal distribution. So that's one thing we need to get used to here, these ideas here of the 68% one standard deviation, 95% two standard deviations, and 99.7% if we look within 3 standard deviations for the data. Now, does this apply to every data set out there? The answer is no, it does not. You first have to have a suspicion that this ought to be applied. And enough study has been done about these SAT math scores that it's pretty safe to apply these normal distribution percentages to that. And I just want to play with these numbers just a little bit more about what they mean. Redraw a normal distribution graph. And again, every time we draw a normal distribution, we need some kind of x-axis. And then we sketch out our best bell-shaped curve. Right in the middle of that bell-shaped curve, we put whatever our mean is. I'm just going to call it x bar. It's the standard sample mean symbol there. And then from there, we count standard deviations on either side. And again, this is kind of like a histogram. Just imagine a whole bunch of columns here. And when we smooth out those columns, it looks like this here. So this is supposed to be a smoothed out histogram is what we're imagining here. A whole bunch of columns, lots of data. And I want to focus on the 68% one. So if I look one standard deviation to the left, and I look one standard deviation to the right of the mean. So the mean is 0 standard deviations. And I'm going 1 to the left, and 1 to the right, and 1 to the left. So these would be z-scores compared to x-scores. In between here, we expect to see 68%. If there's 68% in the middle here, well, there's 100% total, so 100% minus 68% is going to give us 32%. So the tails have 32% to split. So that means this tail over here must have 16% of the data if it's a symmetric bell shape. And this other tail over here, it must also have about 16% of the data. So let's suppose you took a test and you ended up on the test with a z-score of 1. What does that tell us about your score? Well, that's 1 standard deviation above average. So we know that for sure. The other thing I know, based on the belief that these scores are normally distributed, is if this is the edge of the middle 68%, and then there's another 16% below that. So if we consider everybody that got a score less than you, that would be 68 plus 16, which gives us what, 84%, right? I take 68% in the middle, add the 16% below that. On a good day, 8 and 6 is 14, yeah, 84%. So your z-score of 1 also means that you scored better than 84% of the others. I guess better, I should say higher. And anytime I reference a position that marks a percent below, that's called a percentile. So a z-score of 1 is what we call the 84th percentile. That's abbreviated as P with a subscripted 84. So what is the 85th percentile? It's any score that has a z-score of 1, any score that's exactly 1 standard deviation above the mean. So I just want to play around a couple more examples of this relationship between standard deviations, z-scores, and percentiles. And again, the whole assumption when I'm working with this is that my data is normally distributed. Data is normally distributed. All right, so we'll do some more examples of that.